And in that context, you're basically making security a feature.
Yeah. Absolutely. So security can definitely be a value add. Sometimes it's one of those things that you don't recognize the value of. If you're doing it right, no one knows you exist, right? That's or when the security team's doing it right, like you don't know that they're there. But company gets hacked, gets some publicity, like someone just posted the article from the Signal CEO who hacked what's their name? Celebrate something. You get bad publicity like that could really damage your business. All right, it's 10:07. I'm going to get started again. So let me. All right, so this is the part of the lecture where I said we're going to go back to the basics. I know you're several weeks in or several months in now to your Code Platoon journey, so you're probably familiar with a lot of these concepts, but I want to start back at the foundational knowledge. This is really important to me, and a bit of like a pet peeve of mine sometimes is that we jump into security concepts and we try to explain security vulnerabilities and we focus all on the vulnerabilities and the cool, sexy exploits, but we don't have like the foundational knowledge to understand what even causes them to begin with. So I want to start back and focus on web app security education by focusing on web app education to begin with, and understand the underlying security principles, because then the bugs make a lot more sense. And if you don't understand like what's causing these at the foundational level, then trying to fix bugs and security bugs in web apps is like playing whack-a-mole. They keep popping up and you don't know why. And even very experienced developers and pen testers in my field like mix up concepts and don't fully understand like how they work together. So by understanding why the attacks work, you can learn how to defend against them. And that's what I'm going to try to achieve here. So back to the basics here. The fundamental technologies that power the World Wide Web. We're going to talk about the main technologies in the overview and just the differences between them. And so as we start building on these and I use these terms, we can fully understand what's going on here. So HTTP, HTML, CSS, JavaScript, DOM, these terms get thrown around. They all combine together to build modern day web applications, but they're different technologies. They serve different purposes. So HTTP is a plain text protocol. All it is it just defines how data gets transferred between a client and a server. That's what a protocol is. It's well defined. It has like accepted verbs and headers. It's based on plain English words like get and post and head. And it's generally over TCP ports 80 or 443. And 443 is for HTTPS, which is encrypted HTTP. But HTTP is not a language. It's just the way that you define how you're going to send information between 2 points. HTML is a markup language that describes to the browser how to render a page. And it is not a programming language. It's just a definition and a way for how to represent data. So HTML, you shouldn't necessarily say, oh, we're programming in HTML. We're writing HTML, but HTML is no different than XML or JSON. It's just a way to represent data. Sorry, I got a note that there was something in chat, but I can't find my chat window. If there was a question, please just shout it out. The next is CSS, or cascading style sheets. Again, not a programming language. It's a way to represent data. It's metadata that gets associated with the HTML, and it basically just styles it. It tells the browser how to display it, what color it should be, how big it should be, where it should be on the page. So HTML and CSS get sent over HTTP to a browser, and the browser uses the HTML and the CSS to create what's called a document object model. I don't know if this has come up or if you've heard this term before, but the DOM is a very important concept when you're building a web page or a web application. The DOM is ultimately what gets displayed and interacted with by the end user. So everything you see and you click is one big object in the browser called a document object model, and it's like a tree of nodes of HTML and CSS and associated JavaScript, and it gets built into the DOM. So visually, right, www.example.com, Firefox gets the HTML, it gets some CSS, and it renders that page to life and it builds the document object model, and that's what the end user sees. So one big technology missing here is JavaScript. So in the world of web, JavaScript is king. It does everything, and it's becoming ubiquitous, and it's just powering everything in the world right now. As opposed to HTML or CSS, JavaScript is a complete programming language. You can write full programs in JavaScript. So JavaScript is just no different. It's a language like Python or C or C++. And browsers have their own JavaScript engine that executes the loaded JavaScript. When JavaScript is running inside the browser, JavaScript has full read and write control over the DOM. So JavaScript can actually write HTML or CSS and change those dynamically and modify what you see on screen. So when you see like modern web pages that have animations and things happening when you click and things moving around, it's JavaScript dynamically changing what you see by modifying the DOM. JavaScript also has full access to browser storage. So things like cookies also, but browser storage like caches and other local storage and session storage we'll talk about in a minute. And JavaScript can also talk to browser APIs. So modern browsers expose APIs to do things like interact with the webcam or the microphone or fetch your current location. And JavaScript can talk to all of that within the browser. So JavaScript is very, very powerful. Right? It can turn on your webcam. It can listen to your microphone. I'm sure Zoom is powered by JavaScript to some degree. But if we were in like Google Meets or something, that's all JavaScript also. It's happening within the browser. So because JavaScript is a full programming language, I mean, if you think about it in terms of security, this is kind of terrifying. It's like a nightmare. It's basically like any page you go to will execute any JavaScript, and you can just downloading and running any code from the internet anytime. So the browser makers are very aware of this and take extreme care to protect your computer from JavaScript. So they do that by executing JavaScript in a sandbox. There's security boundaries and controls over what JavaScript can actually do when it's inside your browser. And this is gonna be really important. There's a couple different ways that browsers do this. But the first and foremost one is like, if I'm in Chrome and I'm executing JavaScript, JavaScript can never, ever actually interact with my underlying computer. Like JavaScript should not be able to read and write files from my C drive or open up new processes or ports or anything on my computer. Like it should be only confined to Chrome. And every browser has its own sandbox. Those sandboxes are super serious. Anytime there's a vulnerability or a quote unquote sandbox escape by JavaScript, they're usually rewarded with like $1 million bounties and fixed very, very quickly. The other way that that JavaScript is limited, we'll get to in a few slides. But I'll pause there and just make sure everyone's on the same page. Like, does everyone understand the difference between HTTP, HTML, CSS, and then JavaScript, which kind of covers everything? Cool. So I guess in the context of what you all are doing, right? Django is your backend server. All Django is doing is sending HTML and CSS to the browser over HTTP, and embedded in that HTML is the JavaScript, which powers your React application or your front end. Okay, so we're going to be looking a lot at HTTP. When we start doing manual testing, everything that gets done over the internet on a web app is HTTP. So if you haven't seen it before, this is what HTTP looks like. Like I said, it's just a plain text protocol, and we can just connect directly to a website on port 80 and actually write HTTP by hand, and the website and the server will send us HTTP back. So everything is in ASCII, which is great. It makes it easy to read. It also makes it easy to modify. Here, I'm just opening a connection to Google on port 80, and I'm just writing one line of HTTP, telling it to get me the home page and use HTTP 1.0, and Google spits back both headers and body. Headers are special instructions that the browser will understand and take action on. And the body is usually where the HTML is, and that's what the browser will then read and display. Now, really important concept with HTTP is that HTTP is a stateless protocol. And what this means is that as I'm talking to, say, Google, my connection is constantly being closed and reopened. I don't have like a dedicated connection to Google, and Google knows that it's talking to me, and we're just streaming data back and forth. It is a request, response, close, request, response, close. I am making multiple requests to Google, and each one is independent of the previous one. So what that means is that when I'm talking to Google or I'm talking to a server, it doesn't have a memory of like, oh, I already sent Ronnie that, or I've seen this person before. Every single HTTP request is completely independent and standalone and has to be treated as such. So HTTP requests have to include their own identifying information, which is, which we'll talk about is usually done through session cookies. Another important concept is since HTTP is a plain text protocol, certain characters have to be encoded. In HTTP, for example, a new line character means something to the protocol. So you can't just send a new line character by itself if you need to. You have to encode it. And encoding does not equal encrypting. Want to make that very clear. Encoding and encrypting are very different things. Encoding has no security benefits at all. Encoding is just changing text or data from one format to another. Encrypting is actually, changing or enforcing confidentiality or hiding data, but encoding is just changing data. It doesn't actually give you any security. So web apps use various types of encoding, and it's really useful to kind of be familiar with them and identify them on site as you see them. So here's the most common ones. If I take this string here called hello world with an exclamation point, we'll oftentimes see in web applications URL encoding, which looks like a bunch of percents and then an ASCII ASCII hex value. So %48, %65, %6c. This is the string hello world with an exclamation point, URL encoded. Likewise, this is the exact same string, but HTML encoded. It's got ampersands, pound signs, and semicolons. This is the string in just pure ASCII hex. This is the string in base 64. Oftentimes, though, only the special characters are encoded because normal ASCII text is okay. So you'll see like hello, then the space gets encoded to a plus, and the exclamation point gets encoded to a %21. Again, all of these are the exact same data. They're just represented differently. There's no security here. I can just convert this back and forth. So don't think that by putting something secret in base 64, you're making it secret. You're not. You're just changing it to a slightly different format. So session management, like I said, HTTP is a stateless protocol, and that means that servers have no memory. They don't remember if they've talked to you before. They don't remember if they've sent you anything before. Every incoming request to a server is a brand new request to that server. And servers have to accept and parse every request sent to them to decide every time whether or not to process it. So initially, HTTP is operated like this. It was a stateless protocol. There was no concept of like memory or state, but then people wanted to start logging into things, and then they needed to remember that they had been logged in, and the servers needed to remember who they were talking to. So cookies were invented as sort of like a bolt-on hack to the initial HTTP proposal. And cookies are just unique identifiers that a server sends back to a client. And as long as the client sends that cookie with every subsequent request, the server will remember who they're talking to. You can kind of think of cookies as like, you're leaving a theme park and you get like a wristband. And as long as you present that wristband when you're coming back to the entrance, the theme park will remember you and let you back in. When you log into a web application, the server will send you a cookie. As long as you always present that cookie for every subsequent request, the server will remember who you are and let you back in. So they're usually an identifier used to correlate a client state server side. However, they're also used for tracking and for advertising. So cookies are kind of a pain in the ass. Since they were invented, I would say they've kind of been abused and gone beyond their initial intention. And now cookies are just everywhere. And I'm sure you've seen all the pop-ups as you browse sites for GDPR and like, we use cookies and please accept cookies. They're kind of a privacy nightmare because basically they're just little fingerprints that get sent all over the internet so that advertisers and web servers can know who you are and where you've been. And that's because browsers are extremely quote unquote helpful and they will send cookies automatically. So this is not something that's like opt into. If you get a cookie, your browser will always send that cookie for any request that matches it. And we'll see later when we talk about CSRF, like there's some security issues that come with this because browsers are really overly helpful and try to automatically send these when they really shouldn't. Cookies have evolved and there's been some new flags that have been added to browsers, and browsers will treat cookies a little bit more securely. The latest one is same site, which I'll talk a little bit more about later. Only the newest browsers even support this, but really all you need to know is like cookies have been evolving and there's been security improvements to cookies over time. Okay, besides cookies, there's another way that browsers can remember information and send it to servers. And that's through two different types of storage within the browser. So every major browser, Firefox, Chrome, Safari, Edge, Internet Explorer, they have this storage mechanism and they expose APIs to JavaScript to let you write and read data in these storage locations. And they're called local storage and session storage. The main difference between the two, local storage and session storage, is when you close a window, everything in session storage gets erased. So session storage is only there for the length of like you browsing that website. If you open a new window or you close the window, it's all lost. So it's meant for like ephemeral temporary data. Local storage actually saves, and the next time you open a window of the same site, the data will still persist there. So web applications will actually write data into your browser, and if it's in local storage, it'll stay there until it's explicitly cleared out. And while we'll talk a little bit more about this later, there's differences also in what JavaScript can and cannot do with this data. There's ways that you can protect cookies from JavaScript, but you cannot do that with local storage or session storage. The entire purpose of local storage and session storage is for JavaScript to be able to access them. So JavaScript will always have read and write access to local storage and session storage. And cookies are scoped to a domain, but are only available to JavaScript within the origin, whereas browser storage is isolated entirely by the origin. And I'm just calling this out now because I wanted to introduce these terms to start you thinking about it, but these are, and I underlined them, they're very important terms for web security, domain and origin. Just keep that in mind. We will bring it up a little bit later. Okay, now everything is powered by HTTP, right? Every web application that we see is under the hood just making HTTP requests. And browsers are the ones that are making those requests. So Firefox or Chrome, they're initiating and opening a network connection to a server and sending HTTP requests across the wire to the server. And there are two distinct ways that browsers will open that connection and make the HTTP request. The traditional way is through browsing context, they call it, or through HTML. If you go to your address bar in Chrome or Firefox and you type www.google.com and hit enter, that is quote unquote the traditional way of making an HTTP request. When you hit enter, the browser will make an HTTP request to Google and then load the page for you. When that HTML comes back, Google, or your Django application as you're writing it, will include other things in the HTML that the browser needs to go fetch. Things like CSS, things like JavaScript, things like pictures. The browser will load all of those resources to build that whole page for you. So these I kind of call HTML requests because the browser is making these requests based on information that's within the HTML. So all of these are examples of HTML that will cause the browser to automatically make a request. You can do some things automatically, like when a page loads. So if you put a link attribute in here for a style sheet, the browser will make an HTTP request for hello world.css. Likewise, a script source equals will also make an HTTP request for that script. That's how you load JavaScript. And you load your React app, for example, is through an HTML tag like this. Image, iframe, these things, the browser will, as soon as it parses the HTML, go, oh, I need to fetch that resource. Boom, I'll make a request and fetch that resource. Some things, though, require an event, like a user clicking. So a link, for example, an A tag with an href to Google, click here, won't do anything, but if a user clicks here, it'll make a request to Google and change the page. Or a form, inputting your username and hitting submit. When you hit submit, the browser will send an HTML or HTTP request and change the page. So these are the traditional way that browsers make requests, right? The other distinct way is the quote unquote JavaScript way. So like I said, JavaScript is king. I mean, JavaScript is just taking over, like everything is being done through JavaScript now. So browsers also let JavaScript make requests directly. And as you're programming and you're writing your React app or you're writing any JavaScript front end stuff, you can just, whenever you need to, also make a HTTP request. And within browsers, this API is called XML HTTP request, or XHR, or on newer browsers, it can also be called fetch. The key distinction between the previous and way of making requests and this one is that JavaScript can make these requests and responses completely silently in the background. So as a user, I'm on a page and I don't even realize what's happening because JavaScript executes in the background, and I can make a bunch of requests. So here there's a kind of a quick example of just HTML with an inline script and a for loop for I from 0 to 100, and I'm just making a request to a random website. When this page loads, it's going to look like a static page, but in the background, you're making 100 requests and the user does not know. I mean, that's actually great for user experience because this is how modern web pages work. You load the page once, it looks like nothing's happening, or you're just browsing the page and it's just fluid and things are loading and you're switching pages. And in the background, JavaScript is making a ton of requests and data's flying back and forth, but it's hidden from you. And this is what Ajax programming is called, and that's really what the Web 2.0 movement was all about. And like modern web is all Ajax now. It's like one page load and then a million things in the background with JavaScript.
I got a question. Last year there was some news about some websites were utilizing CPUs to crypto mine. Was that essentially equivalent to this, where it was happening in the background without the user knowing?
Exactly. Yep. Yeah. So any page you visit can load and execute JavaScript. And it kind of goes back to that like terrifying nightmare scenario, right? Like, doesn't that sound really scary? And that's why browsers have to make that sandbox super strong, because they don't know if that code is good or bad. So you could visit a bad website and that bad website can give you bad, evil JavaScript, and your browser will just start executing that in the background and you won't know. So that's exactly what happens. You can visit a website and it can download some JavaScript that just starts crypto mining. And it's not necessarily bad, actually. Like, I think there's some sites that are very open with that. It's like a way for websites to kind of make ad revenue instead of like clicking on a link. They're like, hey, if you visit my website, if you don't mind, I'm going to borrow some CPU cycles and mine some cryptocurrency. But the concept is the same. Any website you visit can execute any background JavaScript, and you hope that it's for good, to load the page, for the functionality, to build the animations, to build your timeline as you scroll through Twitter. But it could be something bad. It could be crypto mining. It could be something worse. But it's a good segue into like, how can we lock that down even more? So the browser manufacturers totally recognize the danger of executing arbitrary JavaScript. Any website you visit can give you any JavaScript and the browser will execute that JavaScript, and that's kind of terrifying. So how do they lock it down? Well, browsers address this by limiting what the JavaScript can actually do. So there's two main security boundaries. I already talked about the sandbox. The sandbox says that any JavaScript from evil.com should never, ever be able to escape the browser and talk to my underlying host. Should not ever be able to like access files on my computer or talk to my like CPU directly or processes. It has to be confined within Chrome or Firefox or whatever that sandbox is. But that's not enough. It also puts another sandbox or security boundary around it called the same origin policy. The same origin policy is sort of the foundation of modern web security. So we're going to talk a little bit about it here. It says that JavaScript should only see and access data associated with the origin it was loaded from. What does that mean? Well, we visit www.example.com. This is our origin. We're going to call that our origin. That's a term within browsers. So www.example.com is our origin. The HTML and CSS come back, and JavaScript comes back and starts executing. JavaScript can do whatever it wants, but it's within the origin of example.com. So JavaScript can modify the DOM, meaning it can change what we see and what we interact with. It can talk to our local storage or our session storage. It can talk to our browser APIs. It can even do things with our cookies, but it does it all within this arbitrary security boundary of the origin. JavaScript that is loaded from example.com can never, ever interact with anything related to chase.com. This is the essence of the same origin policy that protects us as we browse the web. So this is the security boundary or the sandbox is based on the origin. And when you think about it, this is really important and makes a lot of sense, because if I go to evil.com or example.com and load some bad JavaScript, yes, it can be bad JavaScript. Yes, it could do crypto mining, but it shouldn't be able to access anything sensitive. It shouldn't be able to talk to my bank account on chase.com. It shouldn't be able to talk to my underlying host and read the files in my documents. It has to be limited in scope and power by the browser sandbox. Now, if we load JavaScript from chase.com for my online banking, that JavaScript can access chase.com, it can access the API, it can access the cookies, but it can't access anything over here. So these are security boundaries within the browser, and it's called the same origin policy.
So,
yep.
I don't know if you're going to talk about this later. Sorry, but
say that again.
Website, if I sign up for a website, but say like the same email and password as my email, is there anything that stops that website from just like stealing my password and hacking my email?
So if you sign up for like a website and you put, me@gmail.com and you type your password in to that website and it's the same password as your Gmail password.
Yep.
If the site is malicious and they're trying to steal your information, no, there's nothing stopping them. That's essentially like, how phishing campaigns work, where they present you with a fake login screen and you type in your email and your password. The server will retrieve your password when you hit submit and then try it on your actual email. So there's definitely, and unfortunately, there's not really any like technical way to prevent that. You have to just trust what website you're actually talking to. You should always make sure you're actually looking at chase.com or gmail.com before you type in your password. So if we didn't have the same origin policy, I hope you recognize that the web would be a very, very dangerous place, because without this SOP, any site could load any bad JavaScript, and that bad JavaScript could pretty much do anything that it wants to. So this over here is just fake pseudocode that would be like an attacker's dream if the same origin policy didn't exist. So imagine you go to my website, ropnop.com, and I load just some simple JavaScript, and this JavaScript is running from ropnop.com, but I make a post request to your bank account and transfer money from you to me. and then I make a request to Amazon.com and I buy myself a MacBook Pro and I ship it to me. This is the kind of stuff that would happen if same origin policy didn't exist. Thankfully, none of this works because the same origin policy exists. The browser will say, hold on, this JavaScript came from ropnop.com and it's trying to talk to chase.com. Nope, kill it. This JavaScript came from ropnop.com and is trying to talk to amazon.com. Nope, kill it. So the browser forces you to operate within the confines of the origin that the JavaScript is loaded from.
So it's actually the browser that's enforcing this?
Yes. Yep. So good point to bring up. Thanks for mentioning, like, we put all of our faith in the brilliant engineers at Google and Mozilla and Apple and Microsoft to make sure their browsers are doing this correctly, which is not misplaced faith. Like, they do it correctly, and we have to give them the credit there. But yes, everything we do online is entirely based on, is the browser itself secure?
So, I mean, can't anybody make a browser?
Yes. And so you're right. I could send you a browser and say, install this browser and use it, and I could disable all the security features. But how is that any different than me sending you a virus over, or a .exe
Sure.
file and saying, hey, install this? If I send you code to execute, it's game over at that point anyway. But as long as you are only downloading the trusted Chrome browser from Google's Chrome, website, you should be safe. Does that make sense?
Yeah.
Yeah, it's a really good point though. It's a good question, because I see this come up, and I've even seen security people call out and be like, well, if I could trick you into hitting this website from a custom browser, it's game over. And the response should be, well, if you can trick me into running a custom browser, it's game over already. Like, you're basically tricking me into running or installing something on my laptop that I shouldn't install.
I mean, has there ever been an instance where someone breaks through the same origin policy on a browser in the past?
Mm-hmm. Yeah, there have been a couple instances in the past where people are able to either break out of the sandbox entirely. So, like, execute JavaScript within Chrome that crashes Chrome and writes code and executes it in Windows, which is running Chrome. Like, that's a sandbox escape. Those usually go for like $1 million for bounties. Like, that's how rare they are, and they're big deals, and they're patched immediately. Same origin policies can also happen, usually through like bad extensions to browsers, things that aren't like the core functionality of the browser, but you install, like, your LastPass extension. You know how you can install extensions into Chrome or Safari. Sometimes those extensions are bad, and the extensions end up violating the same origin policy.
Awesome, thank you.
Yep. Okay, so remember I talked about the terms domain and origin. I use them a lot. Sometimes people use them interchangeably, but they do have slightly different definitions. So we know that the same origin policy says that JavaScript that is loaded from origin A should only ever be able to interact with resources that are also loaded from origin A and cannot interact with origin B. But what is an origin? So let's assume that JavaScript is loaded from https://www.example.com/home/homepage.html. Which of these resources are considered to be the same origin as this? And it's a tough question. It could be one, it could be all, it could be none. But anyone want to take a stab at which one of these do you think the browser would let you talk to?
No.
Probably just log in maybe.
A?
Yeah, just A.
Okay. Anyone else?
Maybe all of them?
Maybe all of them? Yep.
C.
C. Okay. So it's tough. This is tricky. It's hard for even humans to spot. Thankfully, browsers are really good at enforcing this. The answer is B only. So when we talk about origins, browsers are very strict on what constitutes an origin. An origin has to match 3 parts and all 3 parts. It has to match the correct scheme, host, and port. So if JavaScript is loaded from HTTP from this URL, the scheme has to be the same. It has to be HTTPS. The host also has to be the exact same, www.example.com, and the port has to also be the exact same, which with HTTPS is default to 443. So A is not considered part of the same origin because example.com is actually a different host than www.example.com. There's a subdomain missing there. B is the same. It matches the scheme, host, and port. C is not because it's HTTP and not HTTPS. D is not because API.example is different than www.example. And then E is not because 8443 is a different port than 443. So I deliberately tried to trick you all there, but this is a tricky distinction to call out when we're talking about origins. We're talking about origins. Cool. So how is JavaScript loaded from an origin? You know, I talk about this, you know, the browsers are very, very particular. It says this JavaScript is loaded from origin A. Well, what does that mean? Essentially, it means that the JavaScript has to be included somewhere in the HTML that was returned from the server. So the most common way to do this is through the HTML script tag. And I'm sure you've seen this before if you've written HTML or web apps. Script source equals hello.js will cause the browser to fetch hello.js. And then the browser will know that hello.js was loaded from this origin. One interesting aspect of this is it actually doesn't matter if the JavaScript is hosted on a different origin, as long as it's loaded from this origin. So here we can see I'm also loading a script from attacker.ropnop.dev. Even though this JavaScript lives on attacker.com, it was loaded from example.com, and therefore the browser treats it as trusted and loaded from that origin. The other way you can load JavaScript is through actual HTML attributes. There's a lot of different ways to force the browser to load JavaScript. So you can do things like button on click equals, and then put like inline JavaScript code right here, like console.log. That will execute JavaScript and consider that JavaScript trusted from the origin. You can also do things like catch errors, like try to load a bad image and then catch the error and say hello from an error. And when this HTML is loaded, we can see we get 4 different JavaScript outputs. We've loaded JavaScript 4 different ways from 4 different places, but it's all trusted and part of that origin. Okay, so that's kind of a brief overview of web application security and same origin policy. And I chose specifically to focus on same origin policy because it is the backbone of modern web application security. So to know web security, we have to understand HTTP, HTML, and JavaScript and how they kind of all interact and work together. And then, excuse me. And then same origin policy, which governs what not browsers and JavaScript should or should not be able to do. We can break all of our security concerns when we're talking about web application into 2 big categories, client side and server side. Client side vulnerabilities are attacks that target users. They're targeting you and me and our browser. If we visit a site and bad JavaScript comes and executes in our browser, that's a client side vulnerability. But there's also server side vulnerabilities. And these are attacks that target the servers themselves, the providers of the service. It's similar in concept to the same way that you have backend and front end. So you write Django, that's your back end. You write React, that's your front end. They can both have separate security vulnerabilities. It's client side or server side. React is your client side, Django is your server side. So I mentioned Owasp top 10 before. And I'm gonna just show you the Owasp top 10. It's actually being refreshed right now, but it comes out every 4 years. This is the Owasp top 10 from 2017. The top 10 web application risks are injection, broken authentication, sensitive data exposure, XML external entity loading, broken access control, security misconfiguration, cross-site scripting, insecure deserialization, using components with known vulnerabilities, and insufficient logging and monitoring. I won't read all of these. I do recommend everyone to go to the Owasp webpage. There's great cheat sheets and more explanation on each of these. But two quick notes. Injection attacks have been #1 since the inception of Owasp. Never changed. It's always been the #1 most critical risk. Cross-site scripting has also always been part of the top 10 since the inception, although it's moved up and down a few times. And a couple vulnerabilities are new and a couple have dropped out. It's interesting to see things happen here and there. Cross-site request forgery, or CSRF, which we're going to talk about in our deep dive, is no longer in the top 10 for the first time ever, but it's still prevalent enough and interesting enough that I'm going to talk about it. And broadly speaking, we can actually divide up these vulnerabilities into kind of technical or design. I like to think of them this way. It helps me. Technical vulnerabilities are like things that are wrong with your code, and designed vulnerabilities are things that are wrong with like your design or your architecture or your implementation. So technical vulnerabilities are actually like easier to spot with automated code or scanners. But going back to the question earlier about, you know, pen testing and is our manual testers becoming obsolete? No, because they'll always be able to find the designed vulnerabilities. These are weaknesses in your process, logic, or design. And they're much, much harder to spot with scanners or tools. Okay, that's the end of the section on like intro to browser technologies and security. This section is kind of short. I'm going to talk just a little bit about how we manually look for these tests, and then I think we'll take a break and then we'll dive in. We'll do the deep dives of the actual technical vulnerabilities before lunch. I'll pause here though. Any questions going back to that whole section? I don't know how much of that was review or just refreshing knowledge for you or new. Any questions on the same origin policy, JavaScript, HTML, etc.? All right, I will take that as either a good sign or you all are just glazed over. Sorry, I know that's a lot of information, but I will also be sharing the slides, of course, and these are can be a really good reference for you as well. So with that knowledge, I'm going to talk a little bit now on how attackers and testers like ourselves look for vulnerabilities and how we do it, the tools and techniques. Everything's HTTP. At the end of the day, you know, modern web apps, if you go to like twitter.com or facebook.com, they can seem ridiculously complicated, millions of lines of code of JavaScript, you know, all this dynamic refreshing and animations and fetching of data. But at the end of the day, every web application is just a client talking to a server over HTTP. And testing and finding vulns in web apps is always just a matter of reading, sending, and modifying those HTTP requests. So high level, we have a browser like Firefox and a server. We send one HTTP request for like the main page, response comes back. We send another one for the JavaScript, response comes back. We send another one for an image, response comes back. This happens just hundreds or thousands of times a minute and the page is loaded, but it's all just HTTP requests going back and forth, flying back and forth between a browser and a server. So to manually test these apps, it's all about just sending custom HTTP. That's the only thing that actually communicates between the two. So we just have to modify or send our own HTTP. So how can we do that? We could, as you saw in one of my previous screenshots, we can just open a TCP connection manually if we want to Google server and just start dumping data at them, and we can write our own custom HTTP. But that's a pain in the ass. It's really hard to just write manual HTTP by hand. So the better approach is to use a proxy. And more specifically, an intercepting HTTP proxy. So proxies are not just security tools. Proxies are used all the time to route traffic and inspect traffic. They have a lot of different use cases, but we're going to be using a proxy to actually do security testing. And the proxy that we're going to be using is called Burp Suite, but there's several others that are out there. And this is a logo for Burp Suite, just as an FYI. So the way a proxy works is it actually injects itself as a man in the middle between the browser and the server. The browser and the server do not know that the proxy exists. Roughly, they don't know that the proxy exists. So the browser essentially thinks that it's talking directly to the server, and the server thinks that it's talking directly back to the browser, but we are a man in the middle, and we're looking at the traffic going in both directions. So the browser sends the HTTP GET request to the proxy. The proxy can look at that. It can pause, it can drop, it can modify, it can do a bunch of different things, and then it sends it back onto the server. And the server's response comes back into the proxy. Again, we can drop, we can pause, we can modify, and then we send it back to the browser. So with this, proxies, like I said, can let us view, pause, and modify HTTP traffic in transit. And the majority of web app attacks are really just based on sending unexpected HTTP requests to a server that doesn't know how to handle them. So our testing workflow kind of looks like this. We're going to use our browser, and we're going to browse and use the web application normally. And that's going to cause the browser to send normal, expected, quote unquote, good requests. But every now and then, we're going to stop it in our proxy, and we're going to change that good request to a bad request. Just change something, you know, it could be random, we could inject something, we could just make it unexpected and send it to the server. If the server is configured incorrectly or vulnerable, it may respond to this bad request with the technical term, as I call it, is a WTF response. That's just what I kind of like to say is, and if we can get a WTF response from the server, that's what we live for, because WTF responses are usually indications of bad configurations or vulnerabilities. So some of you who especially have done, you know, network monitoring or worked with this stuff before might be thinking to yourself, what about encrypted? Like, what about SSL and TLS? Like, shouldn't this prevent exactly what we're trying to do? And the answer is yes. Good SSL or good TLS is exactly designed to prevent what we're trying to do. It's supposed to be encrypted end to end so that no one can look at the traffic, modify the traffic, or tamper with the traffic. But we can weaken our own security in a sense and do this to ourselves. So we want to test our own app. We want to test our own traffic. We can basically disable TLS verification and weaken the security so that we can get around this limitation. And this only works because we're doing this to ourselves. I want to stress that, like, I cannot do this to you. I can't modify or read your traffic. I can only do it to myself because I'm explicitly letting myself do it. What this looks like is essentially Burp Suite becomes its own SSL encrypted proxy. And the traffic between our browser and the proxy is fully encrypted with SSL. When the traffic hits the proxy decrypts it. And that's how we're able to see it in plain text. But then it re-encrypts it and sends it encrypted to the server. The response comes back encrypted, the proxy decrypts it, we can see it, then it re-encrypts it and sends it back to the browser. So we can do this with encrypted traffic by decrypting it right in the middle and then re-encrypting it when we want to send it. And that's how we're able to break the encryption and see the traffic as we do our testing. And we'll walk through this afternoon how to actually configure this so that we can get around the security warnings and things like that and decrypt the encrypted traffic so we can modify it. So this brings me to my golden rule of web security, right? We talked about those WTF responses. My golden rule of web security is to never, ever, under any circumstance, not even for a second, ever even consider trusting user input. Anytime you are accepting user input, and when I say user input, I mean in this context like HTTP requests, anytime you're accepting input on the server, you can never, ever trust it, and you can never, ever make assumptions that it's what you expect it to be. Because it's too easy for attackers and testers like us to modify it and send bad and send garbage data. So if you are writing your web application and you only ever expect the happy path to be taken, meaning you're writing it being like, oh, I'm expecting a user input here. Well, they would never send that. Like that'd be weird. And you just write it assuming that they'll never send it. Someone's going to send it and you're going to have problems. Great example is you're writing a web application and let's say you expect the user to input their address and you have a field and they submit their zip code. And you write your code assuming that, well, a zip code would never be more than 5 digits. Well, what happens when I fire up Burp Suite and I send you 1 million letters or 40 megabytes of just garbage data in the zip code field? If you're not expecting that and your server is not written to expect it, you could crash, you could have a vulnerability, you could have a problem. That's what I mean when I say don't ever trust user input. Don't assume that just because zip codes are only supposed to be 5 digits, you're only ever going to get 5 digits. It's a bit of a contrived example, but the principle is the same. Write your code to expect and to validate what you think you should get. Okay, that was the short section. So we went another hour. That's the overview on web security and kind of how we do testing and server HTTP responses. The next section is some deep dives into actual vulnerabilities with some code examples, and then we'll try to break for lunch. But let me pause here to see if there's any questions on this. Otherwise, we'll take just another quick bathroom and beverage break, and then we'll run through the deep dive scenarios. Any questions on HTTP testing or proxying?
So using Burp Suite, you're basically just going to create a man-in-the-middle attack.
Exactly. Yep. We are going to man in the middle ourselves. And that's exactly how we're going to do manual testing and verification of our findings.
Can you do more with Burp Suite than with something like Wireshark?
Yes. Yeah. So when we fire up Burp Suite, you'll see Burp Suite is built from the ground up to actually be a web security tool. So it's got a bunch of different bells and whistles and features that pen testers need and use. And Wireshark is also a great tool. Actually works on a lower level, right? Wireshark will capture the full network traffic. So you'll see like the TCP handshakes. You'll see the individual packets flying over the wire. Burp Suite is layer 7 on the OSI model. So in Burp Suite, it will not show, and we don't care about the TCP handshakes, the actual like DNS lookups, all the other network traffic. It's only going to show the HTTP traffic, which is what we need for most web app testing. Now, sometimes there are vulnerabilities that occur lower in the stack, and then you may want to use something like Wireshark or Nmap to do network level vuln scanning, but Burp Suite is only layer 7 HTTP.
Gotcha. Okay.
How does an attacker position themselves to do man-in-the-middle type interception of traffic if they don't, like, how do they introduce Burp Suite to do that?
Mm-hmm. Yeah, that's what I was saying earlier. Really, we're only able, we can only do this to ourselves. So we're going to configure and man in the middle ourselves. Burp Suite is not an attacking tool in the sense that I'm going to use Burp Suite to attack you or your traffic. I'm going to use Burp Suite to analyze my own traffic and find vulnerabilities that way. So when we do web app testing with something like Burp Suite, we are really just testing the security of the server. So we're either going to use Burp Suite to attack the server and not you. So we're talking then about server side attacks. Or we're going to use Burp Suite to find client side attacks and then send them separately. So I'm never using Burp Suite to just like attack someone else. I'm using Burp Suite as like a research tool to help me find things. And then I have to think about other ways to exploit them. Does that answer your question?
Yeah, thank you.
Yep. Yeah, and it's an important thing to call out. As we configure Burp Suite and you get this running, I've seen this a lot actually, where you configure your browser to talk to Burp Suite, or someone with some security background sets this up and then goes and logs into Gmail, and they see their username and password in plain text in Burp Suite. and they think, oh my God, this is a huge vulnerability. I got to disclose this to Google. Well, there's actually no vulnerability there. All you've done is decrypted your own username and password. There's no way for you to do that to someone else. Like, we've deliberately weakened our own security, basically disabled security checks within our browser and our operating system to do this. So if we see things like plain text usernames and passwords, that's because we did that to ourselves. It's not that we're able to do that to everyone who uses Google.
I had a quick question.
Mm-hmm.
So if you've ever seen Silicon Valley, or like you've heard of, they did like a man in the middle type thing where I think they had their own like Wi-Fi routers or whatever. So like rather than people are like at the event, rather than connecting to like the Wi-Fi, they'd kind of direct traffic through your own antenna and then send that off and kind of be in the middle. Is that similar to what this is, or that's something completely different?
No, it's the same concept. Yeah. So what we're going to do is actually much, much simpler, because we can just configure Firefox to talk to Burp Suite. So we don't need to like trick Firefox. It's our own Firefox. It's our own browser. So we can just configure it. What they did is absolutely a real attack, though, of, you know, tricking other people to talk to our proxy. The problem with that approach, and this is going back, like, let's say going back like 10, 15 years, you used to be able to like sit in a coffee shop and spin up like your own Wi-Fi network, have people connect to you, and then look at all their traffic going back and forth and like see sensitive information or start messing with them. Like, I won't admit to doing this when I was a teenager, but it was pretty easy to do. The problem is HTTPS and TLS has essentially eliminated that entirely. And if you look at the statistics for the amount of websites that are using HTTPS compared to 15 years ago, it's like almost 100% now. So proper HTTPS won't let you do this. The reason being, if I tricked your, you know, say we're at a coffee shop and I trick your laptop into connecting to me, and you try to go to gmail.com, your browser will pop up a huge warning. And you've probably seen it before in Chrome and Firefox, right? And it says like, your connection is not secure. Like the certificate is not trusted. This could indicate someone is tampering with your data, and they won't let you allow it, or you have to like explicitly go in and say like, I allow it and I can do it. That's the problem with trying to intercept encrypted traffic. I can't do it to you. Your browser just will pop up a giant warning and say the certificate's untrusted.
If you capture the initial handshake that happens when someone's trying to connect to your router, or if I'm connecting to my own router for the first time and it does that initial handshake and somebody is snooping in on that and they catch that handshake, I think you can listen to the rest of that traffic that happens between that device and the router. Like any secure traffic between there that happens?
Yeah, so there's a couple layers here. So we're talking about different, right? We're talking about different layers of the OSI model. So like if I can capture or force you to like connect to an unsecure Wi-Fi network, I can probably see packets being sent. And that's where someone mentioned Wireshark. We could look in Wireshark and I could probably see the TCP connections going out to like gmail.com. The problem is that your TCP connection to Gmail establishes the tunnel, and then HTTPS is the encrypted layer on top of that. So there's actually multiple layers of encryption here, right? Like for an encrypted Wi-Fi network, layers 3 and 4 are encrypted, and layer 7 is encrypted differently. So we could potentially decrypt the lower layer, but the ultimate HTTPS layer that we're sending our username and password to Gmail is encrypted with TLS, and there's no way to get past that. Sorry, it's hard for me to explain without like drawing this out, but you're thinking like an attacker, which I love, but there's kind of multiple barriers to stop us. The end goal, or the TLDR is like, this is not easy to do. We can't just intercept someone and decrypt their traffic.
Unfortunately, the DoD not being super good about keeping certificates current or ensuring that the public-facing certificate authorities have access to the certificates have encouraged us all to just click OK.
Yep, that's a huge problem. Like users are so accustomed to clicking OK or I trust it that, I mean, everything I just said about sitting at a coffee shop and like, you shouldn't be allowed to do this goes out the window if the user just says, actually, no, I just click OK, just click OK. Like, let me just see my website. They have to disable the security thing. So I would say that's more of a user problem than like a browser problem. The technology is there trying to protect you, but the users are disabling it because they're just annoyed or accustomed to it.
Yeah, and it's a poor security practice on the entire Department of Defense to have so many sites that you end up having to accept the security, the potential security risk as part of your default use of that website.
Yeah, exactly. Which is why, it's always good to call out, and you want to keep your certificates up to date. And if you're ever logging in, like at a hotel or at a coffee shop, and you're trying to log into your online bank, and you see that warning pop up, like that do not click OK. I mean, something's fishy. Like you should never see a bad certificate from Google or a bad certificate from Chase or a bad certificate from really anywhere, like any legitimate website that you're going to do something sensitive with.
A lot of government websites I go on to have bad certificates.
Unfortunately, that doesn't surprise me. Yeah, it shouldn't be this hard. It's gotten easier. It used to actually be hard to get proper SSL certificates. You had to pay for them. But how many of you heard of like Let's Encrypt? Have you heard of Let's Encrypt? It's a free service that you can get properly signed SSL TLS certificates now for free and automatically. And it's becoming much, much easier to get them. So that's why we've seen much more adoption of proper HTTPS and TLS. And it's also why I just discount anyone that says like HTTPS is too hard to configure or too expensive or too computationally intense. There should be no excuse and no reason in 2021 to have an HTTP only website on the internet. Just get a certificate. That's how we prevent all of this man-in-the-middle stuff. It's fine for localhost, which is, you all are, I'm sure, testing your Django servers and running it locally over HTTP, but don't put it on the internet without HTTPS. Awesome. Well, great questions. The next section is cross-site scripting, which is going to get a bit more technical and deep dive. So why don't we take a break? I have to run to the restroom. It's already 11:10. Let's just make this like a 5-minute break. We'll kick it back up at 11:15. All right, so continuing on, I want to build upon the foundations that we've set and actually start explaining some real world web application vulnerabilities in theory, how they work, and then after lunch in our hands-on lab, we'll actually exploit them. So the first is cross-site scripting. Cross-site scripting has always been a part of the Owasp top 10. It's one of the scoured, it's just been a problem basically since JavaScript was invented and websites have been around. So it's very prevalent. You will hear about it all the time. It's a huge risk for any web application project or web application period. At its core, this is the definition of cross-site scripting. Cross-site scripting occurs when an attacker is able to force a victim's browser to execute JavaScript within a trusted origin. That being said, the name cross-site scripting is a terrible name. And if I had magic powers and could go back in time and just beat someone over the head that named this vulnerability, I would not name it cross-site scripting. I don't think that that's like descriptive enough and confuses people because it actually has nothing to do about like quote unquote cross-site. It's all about loading and executing JavaScript within the same site. A better name for cross-site scripting, and a lot of web app security people just call it this now, is content injection. We're essentially just injecting content into a website so that we can load bad JavaScript. Cross-site scripting allows an attacker to completely bypass the same origin policy by getting their JavaScript to run in the same origin as the site they wish to target. So if we remember same origin policy as being like the biggest like security boundary for web for web apps. Cross-site scripting just throws that all out the window. We're bypassing same origin policy. What does this look like in practice? We know that same origin policy, an attacker cannot just execute arbitrary JavaScript and access your data that's on chase.com. So let's say I want to try to target you, a customer of chase.com, and I know that you've been doing your online banking, and so your browser has cookies and sensitive information and access to www.chase.com. Well, if I give you a link to my website and you land on attacker.com, I can't just arbitrarily load JavaScript to talk to chase.com. That's explicitly what the same origin policy is designed to prevent. So I cannot do that. But in a cross-site scripting attack, I smuggle my malicious JavaScript inside a legitimate HTTP response to basically trick your browser into thinking that my JavaScript came from Chase. Here's what that kind of looks like at a high level. We have the green origin, which is chase.com. We have the purple origin, which is attacker.com. I send or smuggle evil JavaScript to chase.com server. Chase.com server loads or sends my evil JavaScript to your browser. To the browser, my evil JavaScript now actually came from chase.com, which is the good origin. So my evil JavaScript gets loaded inside the green origin and now has access to the sensitive data within this origin. I'll pause here and kind of just repeat this because conceptually, I think this is important to understand. And let me know if this isn't clear. But this is what cross-site scripting is able to do. We basically smuggle content in this case being JavaScript. We smuggle content and we trick the browser into thinking that this evil content came from this server so that the browser executes it within this origin and we bypass the same origin policy. It's kind of like, you can think of like the Trojan horse going past the gates, right? We get past the main defenses of same origin policy by smuggling in some malicious stuff and otherwise benign content. Make sense? Cool. So how do we do that, right? That sounds great in theory. Like in practice, what does that even mean, or what does it look like? So there's actually three main techniques to do this, but they're all about the same thing. They're all about smuggling bad malicious code or malicious content in good content. The first is called reflected cross-site scripting. An attacker is able to load JavaScript from a trusted origin by reflecting it up to and back from the server. And this is usually done through sending a crafted link to a victim with the JavaScript payload embedded. Visually, it looks like this. I'm an attacker. I'm going to target like Jeremy. I'm going to send you a link. In that link, I've embedded some bad JavaScript. So it could just look like www.chase.com/XSS, but replace XSS with a bunch of evil JavaScript code. You're going to click that link, and it's going to open your browser, and it's going to send a request to chase.com, and that outgoing request has my bad payload inside of it. Here's where the reflected part comes in. The server is misconfigured and somehow reflects it right back to you. It just echoes it back to you. So that the content comes from chase.com, but my bad payload is reflected back to you. The browser sees this bad payload, but it sees that it came from chase.com, not from attacker.com. So it thinks that this bad payload is actually trusted JavaScript that came from Chase, and it executes it and gives it full permissions that any other normal JavaScript would from chase.com. So in a reflected cross-site scripting attack, I'm usually targeting one person at a time or an individual at a time. And it's going to be like, hey, click this link, or hey, here's an email with like an embedded image. I have to like send it to an individual person. They usually have to take some sort of action like clicking, and it gets reflected right back to them.
Does that have to be like an existing route?
Yeah. So this is a vulnerability on chase.com server. You can't just send it. You know, these are actually difficult to find. So it's not as easy as just sending it to any website and expecting it to bounce back. It would usually be a very specific route on chase.com, and this XSS payload would have to be in a very specific place, and the server is misconfigured to return it back to you without doing any like validation or something. And we'll see some examples and demos of this. As far as I know, there's nothing like this on chase.com. I'm just picking on chase.com because it's sensitive banking information. But if there were something like this on chase.com, it would be pretty serious. So contrast that with the other main technique for cross-site scripting, which is stored cross-site scripting. In stored cross-site scripting, I take my bad payload, my malicious payload, and I store it on the server. And then anyone that visits the server gets that payload executed within their browser. So this is usually done through embedding a payload in a persistent field. A great example is like comments on a blog post. You know, I can write a comment and then anyone who visits that blog post can view the comment, right? That's a persistent field that gets stored in the database for that server. Well, if I can find a vulnerability and store a bad payload on the database, anyone else who goes to that site, anyone who visits the blog post, will get this bad JavaScript payload served up to them. And again, the browser sees that it comes from like chase.com. It thinks that it's good, valid content and executes that content, and we bypass the same origin policy. I like to pause here because there's a great story. I encourage you to Google it, read about it. I'm sure you all remember MySpace, and MySpace let you comment on people's profiles. Well, there was a hacker in the early 2000s named Sammy Kamkar. He's still active. He still releases great research. He found a persistent cross-site scripting vulnerability in MySpace. He was able to embed something on his profile that any MySpace user who visited his profile had malicious JavaScript executed. And that JavaScript was running within the origin of MySpace because it was a cross-site scripting attack. Well, he didn't necessarily do anything evil. All his JavaScript, his evil JavaScript did was add Sammy as a friend, update your profile to say Sammy Kamkar is my hero, and then write the same malicious payload on your profile. So anyone who visited your profile would then get the exact same. So it was a self-propagating like virus, like it kind of infected people's profiles, and everyone's profile switched to Sammy Kamkar is my hero. Well, he unleashed that within 24 hours. He took the entirety of MySpace down. It was something like 30 million people had their profiles changed to Sammy Kamkar is my hero, and he just completely crashed MySpace servers. And it was really the first like publicly documented example of cross-site scripting and how bad it can be. MySpace had to do a ton of cleanup effort, remove this bad content from everyone's profiles, clean up their servers and their vulnerabilities. But you can look up still, you know, I think there's a Wikipedia page on it, like the Sammy worm on MySpace. And it was a cross-site scripting attack that just propagated all over MySpace in the early 2000s. And it was a stored cross-site scripting attack just like this. Okay, the third type of cross-site scripting is a little bit more difficult to understand, but it's becoming a lot more prevalent with modern day web applications. It's called DOM-based cross-site scripting. So I like to try to explain it like this. Most modern web apps today are like 100% JavaScript, probably like 99% JavaScript. There's just like a little bit of HTML, but it loads JavaScript and then everything else is JavaScript. When you visit like chase.com, I don't actually know this, but let's just assume like when you visit a website like chase.com, the server may only give you one file, and it's just one big fat JavaScript file called like app.js. And then the entirety of their web app is inside that file and everything gets executed within that file. So app.js is always trusted. It's executed, it's trusted JavaScript, it runs within the origin of chase.com. In a DOM-based cross-site scripting, we find a vulnerability not within chase.com, but within app.js that lets us essentially execute additional code that app.js will execute. So this is usually done through like embedding cross-site scripting payload in some sort of field that becomes a JavaScript variable that then is executed without validating it. There's a couple different ways. They're much more hard to find, but the idea is we never actually need to talk to or send anything to a server. We are exploiting already trusted JavaScript code to inject additional JavaScript to execute. hopefully
So
that, yeah, go ahead.
if you've got your same origin preventing that, how do you reach out of your origin into a different app.js?
Oh, I see what you're saying. Yeah. So it kind of works the same way. Usually it's going to be like, I have to send you a link. So I'll say like, hey, click this link, and you'll click this link. But one distinction is like, let me go back. Oh, that's a bad example. So do you see the pound sign here, the little hashtag? So that's pretty common as a way to pass information to JavaScript without sending it to the server. So anything that's after a pound sign is considered like accessible to JavaScript, but not sent as part of the request. So we'll see some DOM-based examples where we send malicious content in a comment or a pound sign within a URL. The server doesn't get that information, that doesn't get sent to the server, but the already running JavaScript is configured to look in the address bar and pull out anything that's there. So we're kind of injecting a variable into already running JavaScript that gets executed as opposed to injecting an entire JavaScript app or script.
Interesting.
Yeah, I hope that makes a little sense, and maybe it'll make more sense. I've got an example of this, and we can kind of see it in action. But conceptually, the main thing I just want you all to take away is in a reflected cross-site scripting, I send you a link and follow along with the red XSS payload. The red XSS payload goes up to the server and comes back from the server. In a DOM-based, the red XSS payload does not go to the server. It just goes straight back into the victim's browser. These are nasty because they don't get sent to the server. If you're thinking about this from like a defensive perspective or a blue team perspective, you've got no logs or indication that this attack even happened because it never touched your server. Okay, so if we are testing for cross-site scripting, or if you've ever seen a bug bounty report or a pen test report, you've probably seen alert 1. Pen testers love to use alert 1 as their example cross-site scripting payload. So if you as a tester are able to get a server to pop up and say 1, it means you found cross-site scripting or just the payload that you use. It really has no security severity though, right? This is just a little indication because it's very visual and easy to spot. So alert 1 is just a simple JavaScript command that pops up an alert box that says 1 and has an OK. The important part isn't really the 1, it's the page that says it. So if the browser comes up and says www.chase.com says 1, it means that the origin is www.chase.com or https www.chase.com. So what we've proved or validated here is that we can execute any JavaScript within that origin. We have chosen just visually as a proof of concept to pop up an alert box that says 1, but in reality, an attacker would never ever do this. Their JavaScript payload would be very would take illicit malicious actions and it would be hidden from the user. But this is a way to just pop up very visually, see like, oh, we've got an alert box, we have JavaScript. Just when you see that, know that it means if I can execute an alert box that says 1, I can execute anything I want. Okay, so what can you do about cross-site scripting? Or what can you do, if you find cross-site scripting? Well, it's kind of game over because same origin policy no longer applies. So really the entire basis of like web security when it comes to JavaScript is out the door. So JavaScript controls everything in that origin and the attacker now controls the JavaScript. So attacker controlled JavaScript can therefore read any sensitive data related to that origin, such as cookies or things that are in storage. And it can make requests within that origin using things like AJAX. So you can do all these background requests and you can make requests to transfer money out or make requests to purchase things. And you can do this in the background without the user knowing. I kind of like to think of it as like if you fall victim to a cross-site scripting attack, that browser is infected. You basically have a virus within the origin. You can't trust anything that your browser is doing anymore.
Is it just that website or everything?
Oh yeah, thank you. Yep, exactly. Just for that website. So it's still it's infected within the origin. So chase.com is infected. Does not affect Google, does not affect Facebook, but everything for chase.com within your browser is now infected and cannot be trusted. So in summary, cross-site scripting is really a better term for it would just be content injection. When we find cross-site scripting, what we are able to do is inject content that is malicious and trick the browser into executing it thinking that it's trusted. And since that malicious content comes from the origin, the browser automatically executes it and the same origin policy does not apply. We've smuggled in content through a Trojan horse basically and executed it from within the boundaries of same origin policy. And since JavaScript is so powerful, if an attacker is able to get arbitrary JavaScript execution, he can pretty much do anything a normal logged in user can do within that website, or really read and write anything he wants. So cross-site scripting is full read-write access within an origin. I think that's my last. That's my last slide talking about the extent or impact of cross-site scripting. I'll talk a little bit about how to mitigate it, but any questions on how cross-site scripting is exploited or what it's able to do? Then we'll talk about mitigating it. So mitigating cross-site scripting is fairly straightforward, but hard to get right because it has to happen all the time, right? If you make one mistake, an attacker will find it. So since cross-site scripting is all about injecting the content, it goes back to my golden rule of security. Never, ever trust content that comes from the user. Anything that the user sends you, any requests that you get, you have to validate it. You have to sanitize it. You cannot trust it. You have to treat it as if it's very toxic and take precautions. And the way you do that is through a couple different ways. Validation, which means just reject it if it's unexpected. If you, going back to my zip code example, if you're expecting 5 digits for a zip code and someone sends you 4 megabytes of like the Rickroll video, just kill the request and don't send a response. Just be like, something's wrong, I'm bailing out, I'm abandoning it. So you can write that logic in there and be like, is this 5 digits? If yes, continue. If not, immediately bail out and just stop. That's a good way to protect. Sanitization. That means sometimes you can't just reject, you still have to like accept it, but you can sanitize it. You can remove all the special characters. If someone sends you something that's got like script tags and brackets and JavaScript, you can sanitize that by like stripping out characters and just making it benign text as opposed to actual code. And then the last option is to encode it. You can also escape or encode special characters in the HTML response, which will then still to the user look like it's valid code, but the browser won't treat it as valid code because it'll be encoded and escaped. Thankfully, almost every major framework has built-in mechanisms to protect against this that you can leverage. So on the server side, you want to make sure that any content you send the browser, especially content that came from user input, is properly encoded and validated. And almost all of them either do this automatically or have a framework or function for you to call. In Django, there's a function called escape. And anytime you take input from a user and write it out back in a response, you need to make sure it's escaped. And escape does some encoding and escaping, meaning converting special characters to HTML encoding, or just removing or stripping special things. If you do this, it's impossible to actually execute JavaScript because you can't initiate JavaScript code without these special characters. So if you just strip them or encode them, the browser will not execute it. On the client side, you can also follow the same rule and never write untrusted content directly into the DOM. So if you're writing JavaScript and you find yourself using .innerHTML, which is writing raw HTML into the browser, you're doing something wrong. You should instead use something like inner text, which is a JavaScript function that will treat the data as text and not as code. There's also a great client-side framework called DOM Purify, which is a JavaScript function essentially that you can call on the client side that will do automatic escaping and coding. And most client-side frameworks will do this for you automatically. Excuse me. So y'all are using React. If you do data bindings in React components, this automatically happens. So if you have a React component and you're accepting a prop called my data, and you are writing it, returning it within a header, and you put my data within brackets, React by default will automatically escape and encode anything that goes in here. So as long as you're using like the basic React functionality and using React to write data, you're generally picking up and inheriting really good cross-site scripting protections. Whenever you find yourself doing something manually or trying to fight React to do something manually, be very careful. In fact, React, I think their function, if you want to turn off the automatic encoding and escaping, their function within React, I think, is called dangerously set inner HTML. Like they literally make you write the word danger in your code to make you think that what you're doing is dangerous, which I love. And a lot of frameworks do that. So if you're writing your code and you're writing dangerously set inner HTML, like think about what you're doing. It's probably pretty dangerous. That's it for mitigating cross-site scripting. Is kind of just like the quick dive there. Main takeaways, right? It's content injection. Never trust user input. Anytime you accept user input, make sure you're always escaping it, sanitizing it, or using some sort of framework here to automatically treat it as just plain benign text and not as code. I'll pause for a minute. I'm happy to go back and explain it. That's like a whirlwind tour of cross-site scripting, which could be a whole day class in and of itself, but that's the 10,000 foot view. But any questions or things I can clarify? Cool. All right, then. I'm going to move on to the next class of vulnerability that we're going to look at and exploit later on today, which is cross-site request forgery, or CSRF as it's called. So I like talking about CSRF a lot. I think it's a very cool and underappreciated vulnerability. It is no longer in the Owasp top 10, which I think I mentioned. Like for the first time ever, it came out of the top 10 because we're just seeing it less exploited in the wild. But I like to talk about it because I think it in the context of same origin policy, is a really cool vuln that makes you think about how web applications and browsers work. So CSRF can be thought of as another bypass of the same origin policy. As we know, our good friend, the same origin policy, resources loaded from one origin should not be able to write data to another origin. So our attacker purple origin here, the JavaScript that is loaded from the attacker origin cannot send a request and write data to chase.com because that's a different origin. The browser will actually stop this, and you'll see a little error message in your browser console that says, I did not allow this because same origin policy won't let me. We've already seen with cross-site scripting how we can get around this by essentially smuggling this JavaScript into the other origin, and then we can do it. CSRF takes a slightly different approach. There are two big exceptions to the same origin policy. First of all, the same origin policy only applies to JavaScript. If you remember all the way back to the beginning when I was talking about the different ways that browsers can make requests, JavaScript is only one of two ways. The other way is through HTML. And HTML predates the same origin policy. So HTML requests are actually exempt because they're legacied in, and HTML requests, the browser will not apply the same origin policy to. And with HTML requests, we have cookies. Cookies also predate the same origin policy, and the cookies are also accepted from the same origin policy rule. So CSRF abuses both of this quote unquote legacy behavior of browsers to bypass the same origin policy and write data across to a different origin. So let's see what that looks like. We know, yeah, so this is just kind of what I just said, but basically JavaScript has same origin policy. We can't do that. So we just won't use JavaScript and we'll instead rely purely on HTML and cookies to do what we need to do. And that's called CSRF. Couple things for a CSRF attack to occur. One, it requires a quote unquote state changing request. What this means is that a CSRF attack you can think of as like a blind attack. We can send data, but we cannot see the responses to it. So the CSRF is never used to actually exfiltrate data because we can't see any other responses. CSRF can only be used to like take an action. So whenever we exploit a CSRF attack, it has to be taking some sort of action. What do I mean by an action? I mean something like transferring money out of an account, leaving a comment on a blog post, updating a user's password, something that you're sending a request to the server and the server's actually taking an action. You cannot and would never use CSRF to just try to read data. CSRFs only occur when you're sending a request to perform an action. The other requirement for CSRF is it has to use cookie-based authentication. If your application does not use cookies, you are not susceptible to CSRF, full stop, period. So it has to use cookies. Most applications still do, although a lot of modern apps don't use cookies at all. They use JavaScript tokens. If that's the case, CSRF doesn't apply. And the third requirement is that this requires user interaction. So a victim has to visit an attacker site or click a link. It's not a fully automated attack. There's always an element of some social engineering here. And it abuses three different things. One, we know that HTTP is a stateless protocol.
You freeze for anybody else?
Yep.
He's been attacked.
It's a test. The workshop just started.
We got him.
We gotta unhack.
Okay, can you guys see the slides and hear me okay?
Yep.
Okay, cool. Well, first time ever doing this on my iPad, so I can't see any of you or get chats now, but I want to just try to get through the rest of these slides. And then when we break for lunch, I'll try to get my laptop back online because we'll need it for the labs. Okay, what was the last thing I was saying? I don't know when I lost you. I think I talked to myself for a while. We were just talking about what CSRF attacks require, right?
You start on the abuses part, I think.
Okay, so right, so CSRF abuses the fact that HTTP is stateless. A server is unable to distinguish legitimate requests from illegitimate ones. Any request to a server from a client looks the same to the server. It doesn't know if it actually came from John Smith or if it came from an attacker. And then if we remember, I also stated that browsers are very overly helpful when it comes to cookies. Browsers will just send cookies automatically if anything matches. This is why we're able to get tracked all over the internet by advertisers. But CSRF definitely takes advantage of this because browsers send cookies left and right, and we can abuse cookies to take advantage, to bypass the same origin policy. And it only uses HTML. Same origin policy only applies to JavaScript. So attackers, when they want to use CSRF, say, that's fine, I just won't use JavaScript at all. And they do everything with zero JavaScript. So the anatomy of a CSRF attack kind of looks like this. It always starts, like I mentioned, with some sort of social engineering, like, hey, click this link, and the link leads you back to my site. So I own attacker.com, and I want to try to attack chase.com and steal some money from you or make you perform an illicit action against chase.com. So I'll send you a link and it says, visit my site at attacker.com/CSRF. I'm not really trying to hide it here. If you saw a link that said, go to attacker.com/CSRF, I probably wouldn't click it, but I would hide this in some cat meme or something like that instead. So if you click that link, what's going to happen is your browser is going to make a request to my server. and it's going to fetch and download a CSRF payload. A CSRF payload is nothing more than pure HTML with no JavaScript included. That CSRF HTML is going to include a form with instructions to send data to chase.com. That form will either automatically be submitted, or again, there will be some sort of button on there that you have to click, like click here to see these cute cat pictures. If you click that, it's going to cause your browser to make a post request to chase.com. Now your browser will automatically attach cookies to any outgoing request if it has cookies that match the destination. That's the dangerous part of cookies and the dangerous part of CSRF. So if you are already logged into chase.com, you already have valid cookies for your account on chase.com, and your browser will automatically send them. So that request in green to post/account could be a request that says transfer $100 in quick pay to Ronnie. You didn't mean to send that, but my attacker.com HTML made your browser send that. Because you were already logged in, your browser sent the cookies automatically, and chase.com doesn't know that you didn't mean to send that request. To chase.com, it looks like that is a valid request from you with your session cookie, and it will perform the action. That's the essence of a cross-site request forgery attack. I force your browser to make a request on your behalf without your permission. What does that HTML look like? It's really simple. Like I said, it's just HTML. So this is the example CSRF payload. This is, again, a very contrived example. This is the actual post request to do like Chase Quick Pay, but all it is HTML. Your HTML, this HTML will load from attacker.com. I don't have a cursor on my iPad, but if you kind of follow along, inside this HTML, it says form. So there's an HTML form. The method is post, and the action is pointing to chase.com/account/transfer. So I, as an attacker, have done some reconnaissance. I have found the exact post request that's needed to actually initiate a transfer of money, and I am emulating that with my own HTML form. The input type can be hidden. I don't actually need to expose anything to you. It can automatically be pre-populated, which is what I do here. Its value is ROPNOP, and the amount is 1,000. And then I can either trick you into submitting the form, or I can just write like 2 lines of JavaScript that automatically submit the form when the window loads, which is what that script does there. So the post request will go out from your browser to chase.com/account/transfer. And that request will automatically include any associated cookies. So if you are already logged in and have an active session with chase.com, this action will actually be performed. Chase.com will see that came from you, that you're logged in, everything matched up, and perform the action. Here is a screenshot from Burp Suite showing the actual HTTP that goes out. So that previous payload, just 5 lines of HTML, all I explicitly told it to send was to ROPNOP amount equals 1,000, which is the bottom box. But look at all the other stuff that my browser automatically sent, which is the top red box. Those are all my cookies that are automatically sent to chase.com. So this is the crux of why CSRF is a problem and browsers are overly helpful. The browser just says, I'm going to send everything I have that matches because you probably want that sent. No, we do not want that sent, but you don't really have a choice. So I can trick your browser into sending all of these cookies. And if those cookies log you in or you are already logged in, then the action can actually be performed. Does that make sense? So really, the way to prevent CSRF is, wait, y'all can still hear me, right?
Yep.
Okay, sorry. I like it. I wanted to make sure my Wi-Fi didn't die, or my hotspot didn't die. All right, so the way to prevent CSRF, it really comes down to taking additional controls to compensate for the browser's overly helpful behavior. We can't do this client side. It has to basically be done server side. The server needs to take an additional step to verify that the request is expected. And the traditional defense is through what are called synchronizer tokens. So think about it like this. If I'm writing chase.com and I'm writing their quick pay functionality, there's a general flow I would expect a user to go through, right? Like they should first go to chase.com and then they should click on the quick pay button, and then they would select a recipient, and then they'd enter the amount, and then they would hit submit. So I basically can kind of expect that there would be several requests that should occur before the final request to send the money. If out of the blue, I just got a request to send money and I never got any of the previous requests, that would be very suspicious and likely indicate like a CSRF attack, because the attacker is skipping all those previous steps and jumping right to the final confirmation step. So traditionally, servers did this through what's called kind of a synchronizer token, which is each step of the way as forms are submitted, a random value is sent from the server back to the client. And every time the user goes to like the next step or submits a form, they have to send that random value back to the server. And it's called a synchronizer token because it synchronizes the client and server so they know they're on the same page, they're on the same step of the process. This does require some additional server-side components to remember the state. It needs to remember those random values, it needs to compare the random values and say like, yep, this is expected, the client is on step 2, or this is the form that I sent them and they sent it back, like we're in sync, this is okay, this is okay, this is good. That's the traditional way. That's how CSRF has been defended against for a long, long time. Personally, I think the better or easier method to prevent CSRF is to invoke the same origin policy. So we already know the same origin policy is like very good. The browsers do a really good job of enforcing it. The problem is in CSRF, same origin policy never gets invoked because there's never any JavaScript involved in sending the form. It's one of the prerequisites of a CSRF attack. So if we want to prevent CSRF, one thing we can do is just make sure that each form submission is done over JavaScript instead of HTML. Because if it's done over JavaScript, then the browser takes the additional step of applying same origin policy and helps us out to prevent this type of attack. So let's see what that kind of looks like. As we know, a CSRF has to be done via state changing requests with pure HTML. But if we apply a little bit of JavaScript, then same origin policy applies and we're better protected. So there's two approaches to do that. One are called double submit cookies and one is custom headers. And I'll talk about both of them with some diagrams to explain it. The third approach, which I think is very viable and a good option if you are designing a new application from scratch, is don't use cookies at all. If you don't use cookies, you don't have to worry about CSRF. It's really hard to say for legacy applications don't use cookies because they've been using cookies for 20 years, or that's just how the technology and framework has been built up. But if you have totally greenfield pastures to like build something from scratch, I would strongly consider just not using cookies at all and using something like JSON Web Tokens and pure JavaScript and just not use cookies, and you'll never have to worry about CSRF. This is honestly why CSRF isn't in the top 10 anymore from Owasp, is because more and more applications are not using cookies. That's one of the reasons. More and more applications are just not using cookies, period. So CSRF becomes less of a problem. So here's the first example of using what's called the double submit for CSRF prevention. We have our same HTML form, but this time this is the actual legitimate real form from like chase.com. So this is how chase.com would prevent CSRF by modifying the form to accept the transfer. It still has the same exact like information, like who you want to send the money to and the amount you want to send, but it has an additional hidden field called a CSRF token. And when you hit submit, it actually calls JavaScript and uses JavaScript to send the form. And we can see that if I had my cursor, but if you look on line 14, input type is button, on click equals submit form. That calls a JavaScript function to submit the form as opposed to just submitting the form over pure HTML. And what submit form does is it takes one extra step before it submits the form. It uses JavaScript to read a value from the cookies called CSRF token and set that value in the submission and then send the form. So why is this? Why does this prevent CSRF? Because you require JavaScript to read a cookie value. It means that the JavaScript has to be executed within the origin. Otherwise, same origin policy would not allow that. And we can therefore be assured that this form submission came from within our own origin as opposed to some other. Let me show you what that looks like here. On the server side, we accept an HTTP post request, and we can see that there's identical values in both the cookie and the form body. The CSRF token is a random string that's the exact same. The server can check and compare that if these two values are identical, the request must have been initiated from the same origin and was therefore trusted. If you tried to do this through a classic CSRF example, the request would actually be coming from attacker.com, and the JavaScript on attacker.com would not be able to read the cookie value associated with chase.com. So these values would either be blank or not matched. I hope that makes sense. And if we see it in practice in the lab, maybe it'll make a little bit more sense. This is a really clever way to prevent CSRF by just utilizing same origin policy to our advantage. And most client-side frameworks will automatically do this. I don't know about React off the top of my head, but Angular, for example, will automatically read and send any cookie called XSRF token in every single request. So if you're building something in Angular, and I'm sure React has something similar, you kind of get these protections out of the box. This is how modern JavaScript client-side frameworks prevent CSRF.
Django does it.
Oh yeah, and then Django would do it on the server side also. Yep. So I'm sure Django would then compare these values and make sure that they are the same. The other option here for preventing CSRF is kind of similar. It's just doing it with a custom header. So the reason this works is because only JavaScript and only JavaScript can send custom headers with HTTP. You can never get the browser to send a custom header through pure HTML. That functionality does not and will not ever exist. If you need to send a custom header with your outgoing requests, you have to do it with JavaScript. So if we institute a custom header that has to be set for every single incoming request on our server, we know that if that header is present, that JavaScript sent that header. And if we know that JavaScript sent that header, we know that JavaScript could only have set that header if the JavaScript was already within our trusted origin, so we can trust this request. This is a quick example of what that would look like. Again, a form. We hijack the form input on line 13 and say, if the form is clicked, execute this JavaScript function called submit form. And on line 21, our JavaScript sets request header X sserf token, no CSRF here. It really could be anything, could be foobar 1234, doesn't necessarily matter. And then we send the form. On the server side, we would see an incoming request that would look like this, and we would see a header called X sserf token, no CSRF here. The server could validate that that header is there. And again, like I mentioned, through some logical deduction, we would know that the only way that that header could even have gotten there is if JavaScript sent this request, and the only way JavaScript could have sent this request is if it came from the same origin, so we can trust it and we can defeat CSRF this way. The header is not there, we just reject it entirely. So CSRF, in summary, it abuses legacy behavior, really. It abuses the fact that HTML and cookies predate the same origin policy. And it just uses HTML and cookies to bypass it entirely. It's not really like it's a weakness in the same origin policy. It's just that we never even invoke the same origin policy with what we're doing. And it requires a couple things. Cookies have to be used, and it can only be HTML, no JavaScript. As soon as JavaScript is used, same origin policy comes into play, so we can't use JavaScript. Now, as opposed to cross-site scripting, which is like full read and write access, like I mentioned, CSRF is write only. You can never use CSRF to exfiltrate data. You can only use CSRF to write data or to take an action. And CSRF is pretty easy to prevent nowadays by just either forcing same origin policy via using JavaScript or by using built-in framework protections. I think I've got, oh, I don't. But yeah, someone mentioned like Django has it. I've already talked about Angular, React. Again, all these frameworks usually have built-in protections, either enabled by default or through just like a really simple, set CSRF protection equal to true or something like that. So that's it for CSRF. Of all the ones that I'm going to talk about, like CSRF is probably the trickiest to understand. I hope that was a good introduction. I also hope that maybe after lunch, when we see one being exploited, it'll make a little bit more sense. But any questions on CSRF or cookies?
So basically, we should just avoid setting like tokens and cookies.
I don't like to speak in absolutes like that. There's pros and cons to everything. There's actually like very lively ongoing debate within Owasp right now about like what is preferable, cookies or no cookies. But if you are concerned about CSRF and you're building something from scratch, and you just you can basically design it to not use cookies at all, I would say try it, because if you don't have any cookies, you don't have to worry about CSRF ever. You kind of eliminate one class of vulnerability entirely by not using cookies. But there's drawbacks to that, right? And I'll make the counter argument that I know my peers have made also, which is if you do everything in tokens instead of cookies, then the impact of cross-site scripting can actually be worse. So there's drawbacks to, like cookies can have protections from cross-site scripting, but tokens can protect against CSRF. It's kind of just like pros and cons to each approach. All right. Any other questions on this one? Well, I was hoping to get through, there's one more vulnerability I wanted to talk about, injection attacks. Well, let me throw it to the group. We can either break for lunch right now, and then I can cover this last section after lunch, and then we'll get into the lab. Or I can power through this in like 20 minutes, and then we can break for lunch, and then after lunch, we'll just jump right into the lab. Anyone have a preference?
I'd vote power through, just get to the material, but it's my vote.
Well, then it's one vote to nothing, so I guess you win. All right, if anyone has any objections, speak up. Otherwise, yeah, I'll cover injections in like 15-20 minutes, and then we'll take a lunch break. Cool. So the last class of vulnerability that I'll talk about is injection. If you remember in Owasp top 10, injection is number 1. Injection has always been number 1 and probably always will be number 1 because it's a very critical, devastating vulnerability that affects server-side technologies. At its core, injection is about abusing the server's handling of unexpected or untrusted input. Following Ronnie's golden rule, you should never, ever trust user input. Injection occurs when you don't follow that rule and you take user input and you do something and execute an action using that user's input. So injection is a bit of a catch-all term. It really depends on the technology and use. Probably the most common type of injection, or the one you'll hear thrown around the most, is Sql injection. And that's actually what I think we'll talk about, we'll see in the labs. But there's also command injection, or RCE, which is remote command execution, server-side template injection, LDAP injection, XML injection. It's just a class of vulnerability, which means we've injected data into the server that the server is executing or taking actions on that it should not be. So injection usually or always occurs when a server takes input and translates it. Servers, as we talked about, really only talk HTTP. If you're talking to a web server, you have to talk to it over HTTP. Now, servers have a lot more technologies behind them, like databases, and those databases don't talk to HTTP. Those databases talk SQL, right? Structured query language. So the server is responsible for translating, quote unquote, HTTP to SQL. You would never ever want a browser, a client or a user to talk directly to your database. So your server becomes sort of like the gatekeeper, the guardian that's going to accept HTTP, translate it, make a call on the back end, then take the results, translate them back to HTTP, and send it back to the user. So in this example, this is like a standard login or user lookup. I can send HTTP to the server that says, look up information on the username Ropnop. So my HTTP comes in, and that's standard HTTP format there, right? Key equals value, username equals Ropnop. The server is programmed in such a way, whatever language it's using, to translate the HTTP into a relevant SQL statement and make a database lookup with that SQL statement. So the SQL statement may be, the SQL statement may end up looking something like this. Select star from users where username equals Ropnop. If any of you have written anything in SQL, this is basically saying select every row from a table called users where the username field in that row is equal to the string Ropnop. The database will return all the information about any users named Ropnop, and the server will do another kind of layer of translation to take those, return them in HTTP back to the browser. The problem with this, and where the core of these vulnerabilities lie, is if the server just blindly does the translation between HTTP and, say, SQL in the backend without any validation or security constructs, the user can actually send a valid SQL and trick the server into executing it. So this is called a Sql injection attack, a classic type of vulnerability. Let's say our HTTP request incoming to the server, instead of username equals Ropnop, is username equals Ropnop, single quote, %20 or %20, 1 equals 1, semicolon, dash, dash. That is valid HTTP. The server, if it's written poorly, will take that valid HTTP and just construct a SQL statement. It's the exact same SQL statement, select star from users where username equals Ropnop, but instead of Ropnop, it dropped in this entire string. The special characters there actually mean something to SQL. So I wish I had, oh wait, maybe I can. Oh yeah, I don't know if you can see I'm writing on my iPad with my pencil. Yeah. Cool, that actually works nicely then. So if we look here, we're sending a special character, a single quote over HTTP, and the server translates it and puts the single quote into the SQL statement. The problem is that that actually means something in SQL parlance. It stops the string, and then anything else that's after the single quote gets added to the SQL statement right here. So we've actually been able to trick the server into executing something that it was not meant to execute by quote unquote breaking out of our SQL statement and writing arbitrary SQL. So can anyone tell me what this command now does? It used to be select star from users where username equals Ropnop, but now it's select star from users where username equals Ropnop or 1 equals 1.
Gonna return.
It's gonna return true.
Usernames, right?
Exactly. Yep. I think a couple people said it. If you add or 1 equals 1, that's basically saying or true. That makes your entire statement always true. So this, instead of just returning the single row that has username equals Ropnop, is actually going to return potentially thousands, hundreds of thousands of rows, because we've made our where clause always be true. Now, a couple other things to notice here is we also include this semicolon dash dash. Anyone know what a dash dash means in SQL?
Is that a comment?
Exactly. Yep. So dash dash space is a comment in SQL. So we had to include this because if you look real closely down here, our single quote and semicolon were actually still added by the server. So we had to comment them out. Otherwise, this becomes a bad SQL statement. So we finish our query with the semicolon, and then we add an open-ended comment character, and we tell the server to ignore anything that comes after it. So this is the essence of a SQL injection attack. We are sending some bad input to the server. The server is doing some bad translation and executing SQL, and we've taken control and hijacked what SQL we actually want executed. That's a really simple example. SQL injection gets very complex, and there's some really, really interesting and cool ways you can exploit SQL injection to basically dump the entire database. Once you find a SQL injection, most pen testers will either stop because they've proved it, but if you really want to get creative, there's some automated tools like Sql Map, which is an open source project that's like the Swiss Army knife of SQL injection. This will actually craft and create extremely complex and very cool SQL statements. If you can kind of like read here, I mean, this is like the example payload right here. Union all select null concat some big hex value with null dash dash like other concat. It basically uses algorithms to construct SQL statements that can extract information with Boolean based or time based queries and clauses. End result is you can pretty much read or do anything in the SQL database that you want, as long as you can find one injection point within a SQL statement. You can run almost anything.
Have permissions too.
Right, with permissions as well. So again, going back, to how your system is designed and architected, your web application needs a SQL user, right? It's going to use generally a username and a password to talk to the database. So if you are running your application with the root user for MySQL, well, then a SQL injection means you can execute anything as root on the entire database. But if you have it more locked down so that your application can only talk to specific databases or tables within that database, you're limited by that. So it's a great control to put into place. Thanks for bringing that up. So how do we mitigate SQL injection? Really, how do we mitigate any injection? I'll stress it again, never ever trust user input. So similar to cross-site scripting, we have a couple methods. One is just escape everything, meaning don't ever use special characters, right? The only way that SQL injection is able to work generally is because of quotes, semicolons, dashes, special characters. So if we just remove all the special characters, that's certainly one approach. Not necessarily the best, but it does go a long way. The other approach is to use things like stored procedures or object relational mappers. What this does is basically abstract away you having to write custom SQL. And I'll stress this point too, if you're writing your Django applications or any server-side applications, and you're actually writing like raw SQL statements, strongly reconsider what you're doing. Usually you don't need to do that. You can use classes or objects or safe functions to do what you need to do without having to write raw SQL. If you look at the top little image there, right, this is unsafe Python code, where you're constructing a SQL statement with string interpolation, doing select star from users where username equals %s, and then formatting that string with the username, db.execute, db.fetch all. That's bad. Stop, reconsider that. Instead, like this is Django notation. If you have a user class, user.objects.filter, name equals username, Django does that safely and securely. That's what you should be using as opposed to writing your own SQL. So most frameworks have really good libraries to interact with SQL in a safe way. Don't ever just arbitrarily write SQL and interpolate a string and execute it. You should really try to avoid that. And that extends to not just SQL. Anytime you're executing any sort of command or lookup, like I said, injection goes beyond SQL. There's things like LDAP injection. There's things like XML injection. If you're ever translating something, try to find like a safe class or a framework or an object to do it.
So for injection attacks to be the number one, on the list, is that first method really how like a lot of stuff is written?
Yes, unfortunately. Yeah, they're still very common. You know, most modern frameworks take very good care to avoid that. But I think the reason SQL injection has just always been very prevalent is if you go back to like PHP was like the first major server-side programming language, and then you had your classic like LAMP stack, Linux, Apache, MySQL, PHP. Like PHP didn't really give you the same level of abstraction that Django does. So a lot of PHP apps just constructed SQL by hand with PHP query parameters. That just led to SQL injection being everywhere. And the reason it's number one too, you know, the Owasp top 10 is not a top 10 list of the most common, it's the top 10 of the most critical. So injection may not be the most common vulnerability anymore, but the impacts of it are devastating. Because this is a server-side attack, we're not just targeting like individual users like you or you and trying to, you know, like compromise your session on chase.com. We're compromising and taking control of the entire backend database of chase.com. You can see how that's much more critical and very, very severe. So injection is always number one because it's still around, people still find it pretty frequently, but also because when injection is exploited, it's like full compromise of the backend services. Yep, good questions. All right, so that was it. We powered through injection. We can take a break for lunch, but any questions or other comments on the three vulns that we looked at: cross-site scripting, CSRF, and injection? Nope. Okay, well, it's 12:30, so let's see. Why don't we, instead of an hour lunch, because I kind of got